So, perturbation methods. Alright, so let's start off with, like I said, a simple example. And we will consider the following quadratic equation. Alright, now of course you know the solution to this equation, right? The exact solution is the well-known quadratic formula which you would have studied in school. Right, so this gives us the two exact solutions to this quadratic equation, and where epsilon now is a parameter, and it's a small parameter that we will see. I mean, basically, epsilon here is the same as I showed you in my earlier example. It's a small parameter, and we would like to know for small values of this parameter whether we can approximate these solutions without using the exact solution. But to motivate the method, we start with the exact solution which I've written down. And now if epsilon is small, then we can expand this solution using basically the binomial expansion, right? And we would get 1 plus epsilon squared by 8. So you write this as to the half and then you use binomial expansion. And so you see that you have two approximate solutions. I should use the symbol, approximate symbol, right? As 1 minus epsilon by 2 plus epsilon squared by 8 plus, so I'm stopping at order epsilon cube, right? Because when I apply binomial expansion to go from the under root to the power series, I will have higher order terms which I am right now neglecting. And so to second order, this is one of my solutions. The other, of course, is where I have minus 1 minus epsilon by 2 minus epsilon squared by 8. Alright, so these are the two solutions that basically we obtain exactly, and then we can expand it out. And we see that the approximate solutions for small epsilon have the form of a power series. What that means is constants multiplied by various powers of epsilon added together, almost like a Taylor series. It basically is a Taylor series in this case. Right, so now what we would like to do is, rather than obtaining this approximate expression from the exact solution, in which case the approximate expression has limited value, we would like to obtain the approximate expression directly, pretending like we do not know that there was an exact solution formula available. And this is really the situation in the problems that we are interested in solving, where they aren't amenable to analytical solution. That is, we know no method to solve them analytically, and so we would like to get an approximate solution to them, because the only other recourse is direct numerical simulations, which of course take time, effort, and which you can't be really sure are always right. And so in that sense, a perturbation solution is something that you can use to verify a direct numerical simulation later. And they also offer, like I said, analytical insight, and also allow you to understand the system's behavior across a whole range of different conditions with minimal effort. Alright, so let's see how to proceed. So step 1 in any perturbation process is to assume an expansion. So this is step 1, I should mention, of the expansion method. There's another method that you can use, and that is used, and in fact more often used today with the help of computers, that I will come to next. But right now let's consider the expansion method. So named because its first step is to assume a form for an expansion. Assume an expansion as an approximate solution. So I write x, the unknown solution, as x naught plus x1 times epsilon plus x2 times epsilon square plus, and I can write higher terms, but I'm going to stop at epsilon square or at second order. Okay, so this is the step 1. Step 2 is to substitute the expansion Let me call this equation 2. Let me go up here and call the original governing equation 1. Okay, so to substitute the expansion 2 in 1, and basically you have to compare the powers of epsilon to obtain equations for the expansion coefficients. Okay, so we will see how that goes. So first substitute 2 in 1. If you're watching this lecture, it's a good idea for you to do the calculation along with me, pausing the video where required. So substitute 2 into 1, right, and try to carry out the expansion. So let's just stop at the first 3 terms, like I said. Right, so x square after substituting would become so you will get x naught square, right? So remember you have x plus x, yeah, plus x1 square epsilon square plus x2 square epsilon to the 4 plus 2 times x naught x1 epsilon plus 2 times x naught x2 epsilon square plus 2 times x1 x2 epsilon cube. Right, so all of this comes out just from the first term of the equation. Then you have plus epsilon x, which gives you the following. Right, and the last term of the equation was minus 1. Alright, so now after substituting that here, we get the following expression, which must hold true as we set up to order 2. Now, see, so basically these order 3 terms don't have much value, like epsilon cube, because if we wanted to account for epsilon cube terms, we should have expanded till epsilon cube. But this is a typical feature of perturbation methods. When you take a certain expansion, higher order terms are always generated, but you basically neglect them because they are smaller than the orders you are interested in. So the first step is to equate terms of order 1. So at order 1, right, if I look at all the terms of order 1, let's mark them out. You have x naught square, all of these terms involve epsilon, and you have minus 1. So it must be that x naught square and minus 1, these 2 terms which are not multiplied by epsilon, they have to balance each other and be 0. Why? Because epsilon, like I said, is a small number, right, arbitrarily small number, 0.1, 0.001 or something, and all the terms that have epsilon will be of that order or smaller, which means that x naught and 1 are so much larger than the other terms that there is no way that the sum of all these terms can be 0 unless those 2 first order terms balance each other out at their order. And this is the idea between an order by order balance when you do a power series expansion. So at order epsilon we get this balance, which is nothing but the 0th order problem. So if we had gone to the original equation and said, let me take the case where epsilon is exactly 0, the most simplest version, you just get the 0th order problem. And there you will see that x naught is basically plus minus square root of 1. So we can have 2 solutions, you can see already appearing here, as we know, because the equation is quadratic. Okay, then let's go to the next order, right, at order epsilon to the power 1. Okay, so now we look at all the terms of order epsilon. So you have 2x naught x1, right? I suppress the epsilon because the epsilon will get taken common out, and since epsilon is not 0 by definition, everything multiplying epsilon should balance each other and be 0. And I'll strike off these terms as I write them down here to keep just for bookkeeping. So that's one term of order epsilon. You have another one here plus x naught, and that's it. So this must be 0, which implies, let's say, for x naught equal to plus 1, let's take the positive branch of solutions, right? Then I will have x1 is minus half, right? And then I can similarly go at order epsilon squared now. And which are the terms I would get? I get x1 squared, right? This term is too small. I get plus 2x naught x2, which is x2 is what we want at to find out at this order. This term is order 3, and I have plus x1, and this term is too small. So this must be equal to 0. So since x1 is minus half and x0 is plus 1, I get 2x2 is equal to minus half plus 1 by 4, right? Because I take this to the other side, you get minus x1. Oh, sorry, I get minus x1, which is plus half. Right, so 2x2 x0 is equal to minus x1. Let's write this out properly. Minus x1 squared. Right, so this must be plus half minus 1 by 4, right, which is basically plus half, which implies that x2 is 1 by 8. Alright, very nice. And so now, if we go back to the original solution, if we now try to write down the full solution, so remember x was x0 plus epsilon x1 plus epsilon squared x2 approximately, which is now 1 minus epsilon by 2 plus epsilon squared by 8. This is one possible solution. There's of course the other solution where you take x0 is equal to minus half, right, and you would get the corresponding expressions for the other terms. If you had taken x0 equal to minus 1 here, right, then this would have been plus half, x1 would have been plus half, and then you would have got minus in front of minus 1 by 8. So you would have got minus 1 plus epsilon by 2 sorry, you will get minus 1 minus epsilon by 2, because both x naughts here have a minus sign, right? And then you've got minus epsilon squared by 8. So this is the other solution. And now if you go back up and see, you see we had obtained the exact same solutions by starting with the full exact solution. So you see that this is just a way to verify the perturbation expansion, because we know the exact solution. But even if we did not know this exact formula, we have now obtained an approximate solution to order epsilon square for your root in the limit of small epsilon without doing a numerical calculation, which is the only thing you would be able to do, only thing you would have to do to find the roots if you did not have the exact formula. Okay, so this is a simple, a simple example of just to show you how the mechanics of perturbation methods work. Remember, this I said was the method of expansions. Now there is another method called the Iterator method. The Iterator method, which is just another method to obtain perturbation solutions. You'll ultimately get the same expansion for a given problem, but the way you obtain the expansion is different. And the reason it's useful is that with the use of powerful computers where you can do symbolic computing, it becomes very useful and simplifies. You don't have to worry about doing a lot of algebra, which is very useful when your problems are large and involve PDEs instead of simple algebraic equations. Okay, so let's start again with the same example. Right, but now this time, instead of assuming an expansion, I write x as some initial guess x0 or a guess solution x0 plus a correction. It's a correction assumed small. To be small because, of course, epsilon is small. Okay, so you are writing it, yes, x is, this is like your current guess solution, let's say. That's because remember it's an iterator method. So x0 is sort of the guess with which you start, and you're saying that the guess is close to the true solution, and the error is x tilde. And what we want to do is we want to derive an equation for x tilde that we can iteratively solve until x tilde goes to 0 and leaves us with x0 as the true solution, or so as the solution to the approximate solution to the given order of accuracy. So to do that, let's substitute this this form of the solution into equation 1. So again, I'll get x0 square plus 2x0 x tilde plus x tilde square plus epsilon x0 plus epsilon x tilde minus 1. Remember I said I want to obtain an equation for x tilde. Now if I simply take all the x tilde terms and write them in terms of x0, it won't be useful for me at all, because I will arrive with the original problem itself in fact more complicated form. And if I could solve this full equation, in fact if I could solve the equation for x tilde right now exactly, then I would be able to solve the original equation exactly. So there's no point in what we have done so far. So therefore, for this method to be useful, you have to make an approximation here to get an approximate equation for x tilde. Right? So we don't want to determine the correction to x0 exactly in the first step. Rather, we want some approximate equation that can allow us to calculate x tilde and improve our accuracy iteratively. So to do that, we neglect small x tilde terms and keep only the largest terms. The largest term involving x tilde. So which are the small terms? You see there's 2 x0 x tilde. Now x0 is assumed to be order 1 because I know that the solution at 0th order, which could be my initial guess, is just x0 equal to 1. So this term x tilde is clearly larger than x tilde squared because this is second order. So if x tilde is a small number, let's say 0.1, x tilde square is definitely smaller than just x0 x tilde. So I drop this. Similarly, I will drop this term because it's x tilde multiplying the small parameter epsilon, whereas this is x tilde multiplying the order 1 quantity epsilon. So I drop these two guys, in which case you see I get the equation for x tilde to be equal to 1 by 2 times x0 with the minus sign of x0 squared plus epsilon x0 minus 1. But now this is simply the left hand side of my original equation, and I can write this as minus the residue about the value of x0 by 2x0. And what is the residue? The residue is the sort of error of this equation. If I substitute x equal to x0 here, I will get something that's not exactly equal to 0. That is the residue. And if that residue goes to 0 for any value of x0, that x0 is a solution. And therefore, this now gives me my iterative scheme. So I start with some x0, right? Let's call it x0 at some time step n is substituted into the residue formula, which is basically this formula for x0. And it's not 0 yet because x0 is not the desired approximate solution. So if it's non-zero, I get a correction x tilde, and I can use that x tilde to update x0 to get the next iteration value. And I go back. And you keep repeating this until you obtain that the residue of x0 is 0, in which case the solution will become x. The x0 for which the residue is 0 is my solution to x0 to desired order, which basically means it's equal to, let's say, I should not say 0 here, it's really equal to epsilon to some power, let me call it p, and this will be to desired order. So I'll have the solution correct to all terms epsilon p minus 1 because the residue will involve terms only with epsilon to the p or larger. So if I want a solution like I got before using the expansion method till epsilon square, I should perform this method until the residue involves terms of epsilon cube and larger, which can effectively be taken to be 0 for the purposes of obtaining this approximate solution. Okay, now this iterative method seems at first glance to involve some more extra work to do these iterations, but the main point is this method is something that you can very easily code in a computer, so that once you identify the iteration scheme, you can get the computer to perform these iterations symbolically using symbolic computation, and it will give you the analytical answer. Also, you note that in this expansion method, you had to start with a form of the expansion. And there are problems where guessing, in this case it was relatively simple, and the first guess of taking a power series expansion in powers of epsilon works. But there are problems where instead of powers of epsilon, you have to take the square root of epsilon. Or sometimes you get terms like log epsilon in these expansions. And guessing those a priori can be challenging, although there are kind of methods you can use to motivate different forms of the expansion. But the iterative method doesn't have that problem. Note I didn't have to at any point here guess what the form of the expansion is, merely to obtain this iterative scheme. And as you apply this scheme, different epsilon terms will come automatically into the solution x naught. And so therefore you don't have to guess what the expansion is a priori, and that can be very useful, especially in complex problems. And I'll show you an illustration of this using Mathematica in just a second. Okay, so this is a Mathematica notebook in which I have basically coded up the examples I just showed you just to illustrate the iterative method. Now in this course we will mostly be using the expansion method because we work things out on paper, but I wanted to give you this demonstration so that you know that either in the group project that you'll be working out as part of this course, or later on if you go further in graduate studies and you need to use these kind of techniques, that you can in fact do them very easily today with computing software like Mathematica. And so the algebraic intensity of using perturbation methods should not give you pause when it comes to applying these techniques. Okay, so I'm starting with the same example, except that instead of having epsilon here, I'm doing sine epsilon. This is just because I wanted to show that with Mathematica, you can solve even a complex problem like this in seconds. Now, whereas the earlier problem you had only epsilon, which means when you do the power series expansion, you only get epsilon x, right? So you'll get epsilon x naught, epsilon square x1 and so on, but there are just 3 terms coming out of that. Here sine epsilon has its own infinite power series, and so you'll get many more terms at first order and second order coming out from sine epsilon. Remembering that the power series for sine epsilon is epsilon and then minus epsilon cubed by 3, epsilon to the power 5 and so on. So it's an odd power series expansion. Anyways, so what you do is in Mathematica I first define this to be my quote unquote function where the solution is fun equal to 0, right? And then if you there's a nice command called series in Mathematica which power series expands, or Taylor series expands a function, and I can do that to any order. Here I take it up to the 4th order. So you see it writes it out and then it shows that I have truncated it at the 4th order. I can also take out the coefficients of the different orders using something called coefficient list. So here you see it lists out all the coefficients of my terms till order epsilon to the 4. I'm just rerunning that because I had done something earlier. Anyway, so you see here that all the different powers are there. This is the 0th order term, 1st order, 2nd order and 3rd order terms of just the expansion of the right hand side. Okay, so now with these tools I can do the following. I can take my original equation, right, which was fun, the original expression, and substitute x as a power series just as we had done by hand, and then expand the whole thing in a power series called this function series, and that's what you get. And now you can take the coefficient of this function series and set it to 0 order by order. So at order 0, you get an equation for the 0th order term, and we know the solution to this, if I use Mathematica solve function, is just x naught equal to 1. Here I have taken the positive root. You can also take the negative root. Now at higher orders, by taking the x naught solution to be 1, I can then obtain the equation at higher order at epsilon 1 and substitute x naught is equal to the solution I obtained, and you get the equation for x1. I solve it in Mathematica, you get minus half, and I can repeat this now for higher orders, and then you get the solution. Here I have gone to third order, and you see it matches what we had obtained by hand. Now the nice thing is I can also compute this root for different values of epsilon using find root in Mathematica, and I can then plot them side by side, which is done here. And the blue line is the numerical solution, and the dotted line is what we obtained approximately by perturbation methods. And you see that it matches really well up to epsilon equal to 0.4, and then for larger epsilon it starts to deviate, unsurprisingly. But again, you see that there's a good region over which you have obtained a good analytical, pretty good approximation analytically. Okay, now this is basic. What I showed you here was simply using Mathematica to do what we had exactly done on paper. The only benefit here is once you set this up, if I change sine epsilon to cosine epsilon, and I can just go through all these steps in a second. So once you have solved one such problem, you've solved the entire family. You just have to run your notebook again. Whereas if you're doing it by hand each time, you have to repeat the calculation. And also you're prone to errors. Here the error chances are less because you can just take the final perturbation solution, right, substitute into the original function and check the residue, and if it's of order epsilon less than epsilon 4 and smaller, you know you have the right solution. Anyway, so but now I'll show you something fundamentally different, which is to use the iteration scheme. Okay, so the first step in implementing the iteration scheme is to tell Mathematica that I'm only interested in solutions up to order epsilon cube. In this case, I could have done epsilon square also. Let's go to epsilon cube because I had gone to epsilon cube in the expansion method above. Okay, so there is this command in Mathematica which basically tells Mathematica that, hey, see, if you see epsilon to some power n where n is greater than 3, you set it to 0. So the benefit of this is when you are doing the iterative scheme and when higher powers in epsilon are being generated, Mathematica will set it to 0 immediately because we are basically treating those higher powers as 0 in this context. And if you want to go to higher powers, you can always increase this value of n. So this greatly aids Mathematica in getting the solution quickly because it doesn't have to deal with unwanted high order terms. Okay, now remember that in the what we would have to do is still go to paper and derive the iterative formula, which we said was right here, right? The new x tilde is the residual at x naught divided by 2x naught. So then all we have to do is specify x naught. I start x naught equal to 1, the natural thing to start with, which is the solution of the simple problem when epsilon is 0. So x naught is initially equal to 1, that's like my initial starting guess. I then compute the residual, and you see it's epsilon minus epsilon cubed by 6. Of course, there would be higher order terms which are now dropped because of this command. Okay, this residual, which I note till a third order, is then used to calculate the new x tilde. So that's my new x tilde, and I calculate the x naught now. So you see I have got x naught, this is the current value of x naught is shown here. I then go back and calculate the residual with this new updated x naught, and you see the residue will become smaller. It's now gone from order epsilon to epsilon squared. I then calculate the updated x naught, I go back, it's now become order 3. Right, it's order 3, I come back up here, and now it's 0, and you get the solution. So it's showing the residue as 0 because of course it's basically saying all the terms are epsilon 4 and smaller, and this is the solution which will match exactly with the solution we have here. And you see at no point in this procedure did I have to specify the form of the expansion, whereas here I had to specify the form of the expansion, substitute, collect coefficients, and do lots of other stuff. So from a computational perspective, from the perspective of the human user, it's much easier to do the iterative scheme. You just set up the scheme and then let the computer obtain the series iteratively, and you also don't have to guess what the expansion form is. So the benefit, of course, is that the computational software does most of the work, you can be sure the calculation will be 0 because the residual will go to 0. And actually there are different types of iteration schemes. The one I set is 1, but you could have come up with a different scheme that's not unique. But what will happen is when you get the right approximate perturbation solution, the residue will become 0. And like I said again, the guess for the expansion is not required. And there are problems where this is useful because, as I mentioned, sometimes the expansion, rather than being in powers of epsilon, is in powers of square root of epsilon or other kinds of non-integral powers. And in PD problems and so on, you can get even more complex types of expansions. Okay, so with that, we will pause our Mathematica demo and go back to paper and wind up this lecture by considering a case of singular perturbation.